Hello, friends. Welcome back to my YouTube channel. Welcome to the 44th part of my discussion on distillation. And as I said in my previous video, I will be making 3 videos on simple distillation. The objective is to discuss the method where XW can be found out by using the Rayleigh's equation. So in my previous video, that is 43rd part, I had discussed the analytical solution for the Rayleigh's equation. And today I'll be discussing numerical number 4. Why this is numerical number 4? Because this is the fourth numerical on the topic of simple distillation. And in this numerical, we will learn to find XW, that is the composition or the mole fraction of the more volatile component in the bottom product graphically. So that is my plan for this video. Okay, so we will start by looking at the numerical statement. So you have a liquid solution containing 50 mole percent of N-heptane and 50 mole percent of N-octane, and this solution is subjected to a differential distillation at atmospheric pressure. 60% of the original liquid solution gets distilled in the process. Compute the composition of the distillate and the residue, and out of the two components, N-heptane is the more volatile component. So which component is more volatile? We know that it is given in the problem statement. Along with this, the VLE data is given to us. The VLE data is like this. You have different values of X and corresponding values of Y, which are in equilibrium with each other. So you can quickly go through these values. So based on this information or using this information, we are supposed to find out the composition of the distillate and the residue. That is, we are supposed to find out XD and XW. A simple task, but we will be learning how to find out XW. So you have a liquid solution, and that liquid solution has two components in it. 50 mole percent of N-heptane, which is the more volatile component, and 50 mole percent of N-octane. And this liquid solution is subjected to a differential distillation at atmospheric pressure. And in this process, 60% of the original liquid solution gets distilled. And if this is happening, we are supposed to compute the composition of the distillate and the residue. And they have provided us the VLE data. We are going to use this VLE data for getting our final answer. So first of all, let us collect the given data. The components involved, you have two components, N-heptane, N-octane, and they are saying, or out of this two, N-heptane is the more volatile component. This information is provided to us. The feed solution, it is a liquid solution of two components. Of these two components, N-heptane, we are going to denote that by A, and N-octane, which we are going to denote by B. XF is provided to us, that is the mole fraction of A in the feed. Mole fraction of the more volatile component in the feed, that is given to us. It is 50 mole percent. What is given to us is the percentage composition. So 50% mole of A. This is given to us, and we know how to convert percentage mole into mole fraction. You just have to divide this with 100, and that gives us XF as 0.5. Then differential distillation is to be used, or the other name, differential distillation, this is the other name for simple distillation. So in the problem statement, they have said that the feed solution is to be differentially distilled. That means differential distillation is to be used, and differential distillation is nothing but simple distillation. In this particular operation, 60% of the feed solution is distilled. So that is provided to us. This information is given to us and we are going to use that. The VLE data is also provided to us. So based on this, what are we supposed to find? We have to find the composition of the distillate, that is XD, and the composition of the bottom product, that is XW. Feed solution, composition of the feed is given, then percentage of the feed, percentage of the original feed solution that is getting distilled, that is provided to us. VLE data is given to us, and then we have to find XD and XW. Okay, now let us solve the numerical. Now, since we don't know the quantity of feed or amount of feed, we have to start with a suitable basis. And the most suitable basis is F is equal to 100 kilo. So we are going to do our calculations for a basis of 100 kilomole. F is 100 kilomole. Now, first step would be to get D and W. And for that, first we will use the information that is given to us. What is the information? 60% of the original feed solution is distilled. So what is the meaning of this, or how to use this information? D is 0.6 times of F. That is 60% of the feed is getting converted to distillate. So simply mathematically this would be expressed in this way. D is equal to 0.6 F. So F is 100, the basis that we have chosen. So therefore D will be equal to 0.6 into 100. That gives us D as 60 kilomole. And for this amount of distillate, let us get the amount of residue. And for that we are going to use the total material balance. So total material balance is F is equal to D plus W. Steady state total material balance. Input is equal to output. So F we know, D we calculated simply. Out of 100, if 60 kilomole, out of 100 kilomole, if 60 kilomole are getting converted, or they are removed as distillate, the remaining 40 kilomole will be removed as residue. Simple thing. And you can follow this with the help of the total material balance, steady state total material balance. So F is equal to D plus W, that is 100 is equal to 60 plus W, that is 100 minus 60 is equal to W, that gives us W as 40 kilomole. So we have calculated the two quantities. So first we got D 60 kilomole and W 40 kilomole. Then let us consider the material balance for A, the more volatile component, N heptane, steady state material balance. So it is F into XF, that is equal to D into XD plus W into XW. So F is 100, XF is 0.5, so 100 into 0.5. D we calculated 60, into XD we don't know, plus W we calculated 40 kilomole, into XW that we don't know. So that is 50 is equal to 60 XD plus 40 XW. So if you look at this equation, you'll find two unknowns in it. Which are those two unknowns? XD and XW. So you cannot solve as it is. And if you have to consider the material balance, total material balance, F is equal to D plus W. So this equation doesn't have XD and XW in it. So you cannot think of solving them simultaneously. So the fact is you have one equation and there are two unknowns. And we have to use Rayleigh's equation for getting these unknowns, XD and XW. Why Rayleigh's equation? Because the governing equation for simple distillation is the Rayleigh's equation. I have derived it in my earlier video on simple distillation. You please watch that video. I'm giving link to that video in the description section. So let us first calculate XW, and for calculating XW we are going to use Rayleigh's equation, and that is what we are going to learn in this, how to get XW using Rayleigh's equation. Rayleigh's equation is ln of f by w is equal to integration from xw to xf dx upon y minus x. So f and w, they are known to us. Xf is known. You have the equilibrium data, and now you have to fit the curve. We have to calculate the integral. That means you know the value of the integral. If you look at the left hand side, you have on the left hand side you have ln of f by w. F and w, they are known. That means the left hand side is known. That means you know the value of the integral. Now you have to get its lower limit, xw. That is the task, and we are going to do it graphically. That means we are going to fit the area under the curve such that this area ln of f by w, this area lies within the two limits. One limit is known to us, the other limit we are going to get. So that is the idea. You have to fit the known area and get the limit. In one sentence, you can understand the concept in this way. Okay, so we are calculating XW, and for that we are going to use the Rayleigh's equation. ln of f by w is equal to integration from xw to xf dx upon y minus x. F is 100 kilomole, w is 40 kilomole. So therefore, you have ln of 100 by 40 is equal to integration from xw to xf dx upon y minus x. And ln 100 upon 40 is 2.5. So it would be ln of 2.5 is equal to integration from xw to xf dx upon y minus x. So by natural logarithm of 2.5 is 0.92. So 0.92 is equal to integration from xw to xf dx upon y minus x. So thus we need to, or we know the area under the curve. The area under the curve, and that is obtained by plotting 1 by x versus x. So you must be remembering the graph is plotted in this way. On y-axis you are going to plot 1 upon y minus x, and on the x-axis you are going to plot x. So this limit is xf, and now you know the area under the curve, that is to be fitted between xf and xw. So now you are going to use your skill to fit this area and get the limit, get the lower limit. So you'll be fitting the area and then you'll be getting the lower limit, and that will be xw. So this is the approach. You need to plot the graph, you need to fit the area, in this case it is 0.92, and get the value of xw. So let us do that. So for that we need to just get additional data. We have the VLE data. From that we need additional data, and we are going to generate that. So XW is found out by trial and error. By trial and error, because you have to fit the area, in this case 0.92, by trial and error. So you have x values, you have y values that are given to us. We will be calculating y minus x for each set, and then we will be calculating 1 upon y minus x. So first is 0.5, 0.689, y minus x is 0.189, and 1 upon y minus x is 5.29. So accordingly, the remaining values are obtained. So for each value of x and y, we are getting corresponding y minus x and then 1 upon y minus x. So we need this table for plotting the graph. 1 upon, I just erase that. For plotting the graph, we need 1 upon y minus x and x. And we are going to get a curve like this. Okay, so that is the approach. You have to fit the calculated area or the known area under the curve and get the lower limit, xw in this case. Okay, so first let us plot the graph. So I have selected the scale depending on the values that I have got in the table. So on x-axis we are going to plot x, and on y-axis we are going to plot 1 upon y minus x. And the data that was obtained fits like this. So you get a curve like this. So area to be fitted, it is 0.92. I'm denoting it by capital A. So capital A is 0.92. Area limits, the limits between which this area has to be fitted, xf and xw. Out of that, xf is known to us, xf is 0.5 and xw is to be found out. And we are going to do that by trial and error. And let us now understand how to fit the area between the limits and get the value of xw. So for that, I am considering a small square on the graph, the smallest square, and I am going to calculate its area. So on x-axis, the length is 0.02. So area of a small square is obtained like this. So it is 0.2. On y-axis, the length of the square is 0.2 because it is 1 divided by 5. So that you can check, this 1 centimeter is equal to 1 and there are 5 small divisions. So value of one small division will be 1 upon 5 and that is 0.2. So that's why the area is one dimension for calculating the area is 0.2. Now just look on the x-axis. So 1 centimeter is 0.2 and there are 0.1 and there are 5 small divisions. So it will be 0.1 divided by 5, which is 0.02. So that's why area of the small square is 0.2 into 0.02, which comes out to be 0.004. So what you can do, you can also consider this bigger square and get the area for that. So for example, this square, if you consider this square, area of this square would be 1 into 0.1, that is 0.1. So it is up to you. I have considered, in order to get more accurate results, I have considered the small square. An area of one such small square is 0.2 into 0.02. That is equal to 0.004. Okay. Now this area, the total area, will be occupied by such small squares, and we know area of one square. So you can easily get the number of such squares that will be required to fit this area. And how to get that number of small squares? It will be total area divided by area of one square. So that will give number of small square. Total area to be fitted is 0.92. Area of one small square is 0.004. In this way, that gives us 230 number of small squares. You need to fit 230 small squares like this and get xw. If you are fitting 230 small squares between xf and the XW that you need to decide by trial and error, you are fitting this area. I hope this is clear to you. So area to be fitted is 0.92. It is to be fitted between the limits XF and XW. XF is known to us, 0.5. XW we have to find out by trial and error. And how to fit that? For that, I have considered the smallest square on the graph. So it has an area of 0.2 into 0.02, that is 0.004. And if this is the area of the smallest square, then number of this small squares will be the total area to be fitted divided by the area of single square. So that is 0.992 divided by 0.004, that is equal to 230. So now our task is to fit 230 such small squares under this curve and get XW. Okay, now let us fit the area between the limits. Number of small squares that are to be fitted is 230, and the upper limit is known to us, XF. So I'll draw a vertical line at X is equal to XF, that is 0.5. And now you have to fit those 230 squares. Now the idea is you select one area. You have to select such an area. For example, I have selected this square. So you have to select the size of the square will be such that the vertical distance, the entire vertical distance on the under the curve will be covered by those squares. So I'm selecting this square. So how many small squares are there in this selected square? You can check. So you have 5 vertically and 5 horizontally. So it is 5 into 5, 25. So if I am selecting this square, I am taking care of 25 small squares. So with this, I can go vertically and cover the entire distance under the curve. So if I can cover the entire distance. So how many squares will be covered in that? 25 plus 25, 50 plus 25, 75 plus 25, 100 plus 25, 125, and this will be additional. So if you count, you'll come to know that the total number of small squares that are covered in this region, they are 132.5. So you just remember one thing, you are going to start at XF. You know the number of squares. Over here I have selected small squares. You can also do calculations by considering the bigger square. It is up to you. So I'm starting with selecting a square of such a size which will cover the entire vertical distance under the curve. So out of 230 number of small squares, by selecting this size of square, I have covered the entire vertical distance, and by doing that, I have accommodated 132.5 small squares. Now the remaining squares will have to be accommodated and accordingly, depending on the remaining number of squares, you have to select the size of the region that you are going to cover. So if I consider this square, this region, now it is a rectangle. So on horizontally, there are 3.5 small divisions, small squares, and vertically there are 5 small squares. So if for one selected region I'll be covering 5 into 3.5 small squares. 5 into 3.5 small squares. Again, the size is selected so that I'll be able to cover the entire vertical distance under the curve. So if I do that, I'm able to cover the entire vertical distance, and in doing so, I'll be accommodating 96.75 number of small squares. 96.75 number of small squares. Now let me check the total number of squares that I have covered. So 132.5 plus 96.75. So that gives me total number of squares that I have covered is 229.5, which is approximately 230. So the other 0.5 will be covered in the regions and the small regions that are left out in the counting. So that means I will be, when I reach this end or when I reach this point, I have covered almost all, that is 230 number of small squares. So that will be the lower limit. I have fitted the area between the two limits, and by fitting the known area, I have got the lower limit. What is that lower limit? 0.33. 0.33, that is nothing but XW. So after fitting the area under the curve, XW comes out to be 0.33, and that was the objective calculation of XW. I hope you have understood it. You fit the area under the curve by selecting regions such that you are able to cover the entire vertical distance under the curve. That is the approach. And of course, you have to do it by trial and error. While deciding the size of such regions, you have to use use a trial and error approach. The most important requirement is whatever size you select, with that size, the entire vertical distance should be covered. That is important. I hope you have understood it. If you have any doubts, you please mention them in the comment section. I'll answer your questions. Okay, so after getting XW, let us get XD. For that, we are going to use steady state material balance, or E. We obtained this equation earlier. 50 is equal to 60D plus 40 XW. XW is 0.33. That is, therefore, 50 is equal to 60 into XD plus 40 into 0.33. That is, 50 is equal to 60 XD plus 13.2. That is, 60 XD is equal to 50 minus 13.2. That is, 60 XD is equal to 36.8. That is, XD is equal to 36.8 divided by 60. That gives us XD as 0.61. So in this way, we got both the values. It is XW 0.33 and XD 0.61. So with this, I end my discussion for this particular video. Here, I hope you have learned how to find out XW using Rayleigh's equation. We learn the graphical method. I hope you have understood. If you have any doubts, you please mention them in the comment section. I'll answer your questions. So, thanks for watching my video. Do subscribe to my channel. Tell your friends to subscribe to it. And I'm sure you must have learned how to find out XW using Rayleigh's equation. Hope to see you in my next video, where I'll be discussing one more numerical based on simple distillation, where I'll be discussing how to use the analytical solution to get XW. Thank you. Have a nice day.